So hence it is called as a RC coupled amplifier. Now, so let me first deal with your single stage CE amplifier. Now, in this single stage CE amplifier, so your transistor is the most important parameter or a component, so which can amplify your signal, weakest signal. So now here, when only one transistor is associated with your circuitry, biasing circuitry, used for amplifying your weak signals, it is called as a single stage transistor amplifier. So a weak amplifier consists of many number of stages. So, so we have to cascade number of the same type of your CE amplifier stages. With that, we can get more voltage gain. And now for the analysis purpose, so in order to analyze your voltage gain, power gain, to calculate your voltage gain and power gain as well as your current gain, so we have to analyze each circuit by just dividing or by splitting your the total cascaded stages into a single stage. After analyzing the first stage, then the same we can implement for the next coming stages of n number of stages. Then we'll calculate the overall voltage gains and current gain as well as the power gain of your amplifier. Now, by analyzing carefully only one single stage amplifier, we can repeat the same values because we are taking the same components on those second stages to nth number of stage. So we can effectively analyze the total complex circuit by analyzing a single stage circuit. So therefore, first the single stage amplifier analysis is of great value of understanding in practical amplifier circuits. So let me first analyze your single stage CE amplifier, the DC analysis, as well as the AC analysis. So what are the components needed to connect it as it is functioning like an amplifier? So we have to use some biasing circuits as well as we have to use some coupling capacitors. So what is the need of those coupling capacitors? Those are the things. Let me learn it today's session. So what are the circuit elements of transistor amplifiers? So a transistor can amplify faithful amplification without distortion. The output we can obtain by connecting your amplifier in a using your proper biasing circuit, as well as we have to use some circuit elements in order to function like a single stage transistor amplifier. So now those circuit elements of your single stage CE amplifier is, first one is the biasing circuit, second one is your an input capacitor, and the third one will be your emitter bypass capacitor. So what are the need of these three circuit elements that we will go in detail. So biasing circuit, as we already discussed, so this biasing can stabilize your operating point. So now, so which can it can establish a proper operating point, so which ensures the faithful amplification of your signal. So generally the potential divider method of biasing we are going to employ in your single stage CE amplifier, as other methods which are emitter bias, fixed biasing, emitter bias, then you have your collector to base bias, collector to emitter bias. So those all five, the remaining four biasing techniques are having the less the stability is very poor in those methods. Only the voltage divider or cell bias. So we will also call the voltage divider or potential divider method, or we'll call that as a self biasing method. So which is employed because the stability factor is near to the ideal value of your actual stability factor, which is equal to 1. So we can obtain it in here only in potential divider method of biasing. Hence we prefer the biasing circuit, and it is also very simple to construct using here two resistors R1 and R2, which can act like a voltage divider biasing network, as well as one emitter resistor we connected to your emitter, as well as one capacitor, bypass capacitor will connected the emitter resistor for compensation. So with the additional DC voltage, so we can simply construct a biasing circuit of voltage divider. Next, The second thing is an input capacitor we needed. This input capacitor which is coupled at the base of your transistor. Other end is connected to the signal source, so AC signal source. So if it is not used, the signal source resistance will change the biasing conditions. So every source would have some series input resistance, so signal input resistance. So that can change here if I am connecting that as in series with my base terminal. So that input resistance is also included. So as to calculate your QGNT values. So now when this input resistance of signal source is added to the base input or the input of your transistor, then it might be, so the QGN point may vary from your center, so which can we can get your distorted output at the amplifier. So in order to avoid that, we are going to connect your coupling capacitor. So a coupling capacitor Cin is connected at the signal source, other end is connected to the base of your transistor. Now not only this, so this capacitor is also allows the AC signal to flow but isolates the signal source from the biasing circuit. So we also connected your DC signal through your potential divider network R1 and R2, and through your capacitor we are connected your AC. So if I am not using any capacitor over there, then that DC might added with your AC signal. So hence there is a overlap. So there is an additional or series connection between your DC and the AC signal sources. So in order to avoid that, so your capacitor, coupling capacitor may isolate your signal source, your input signal source from your DC or the biasing circuit. So for this, because of these two reasons, so we have to connect the coupling capacitor at the input of your transistor. So next a coupling capacitor is connected at the output as well. So this can couple at a collector terminal of your transistor, or we can couple that as a coupling capacitor, which can transfer your output of the first amplifier stage to the input of your next amplifier stage. So using your coupling capacitor, if it is not used, the bias conditions of your first stage will drastically changed. So hence, so it can disturb the second stage. So second stage output biasing. Hence, in order to avoid that, so no need, we should not couple your any DC signal from the first stage to the second stage. So in a multi-stage amplifier, hence we are going to utilize a coupling capacitor at the collector terminal of your first stage or at the CE amplifier stage. So this capacitor also isolates your DC of one stage from the next, but allows the passage of your AC signal. So output of where the output is having the AC signal, the first stage is having your output of AC signal that can be transferred without any attenuation through the coupling capacitor, but the DC signals which are due to your biasing of first stage may not be coupled to as an input to the second stage. So that can be done with the use of your coupling capacitor. So this can block your first stage DC amount of signals at the output. So now next parameter in your amplifier is your emitter bypass capacitor. Now, so as to provide your temperature, so now if temperature increases, then amount of collector current changes. So in order to control that, so we have to connect a emitter resistor. Emitter resistor is connected at the emitter terminal. So the amount of voltage drop, so which is occurred at the emitter resistor, can compensate the increase or a decrease of collector current by varying its emitter voltage. The base voltage is controlled. When the base voltage is controlled, obviously our base current is controlled, may decrease or increase based on the amount of base voltage, and that base voltage depends on the emitter voltage. So now IB is directly proportional to your IC. So if there is any change in the IB, that is reflected on your collector current. By this way, we can connect your emitter resistor. But so when I am applying an AC signal, so then that AC signal drop, the collector current may also transfer through the emitter resistor. So due to that, the amount of voltage will be more. So almost the output will be lower. So if I am connecting like that, so if I put out only the resistor, so then so how to avoid this problem is just by connecting a capacitor in shunt with your emitter resistor, so which we call it as a bypass capacitor, emitter bypass capacitor. So the AC signals are transferred through that capacitor, whereas the DC signals are blocked by the capacitor. So like this. So here the usage of your emitter bypass capacitor, where it is in parallel with your emitter resistance. Next, this capacitor provides a low reactance path for the amplified AC signals. If it is not used, then the amplified AC signal flowing through the RE will cause a voltage drop across it, thereby reduces the output voltage. So in order to nullify the reduction in the output voltage, so due to the emitter resistor, we connected a emitter bypass capacitor. So that emitter bypass capacitor can offer a low resistance path for the AC signals. So um, the reduction in the output voltage is reduced by connecting a emitter bypass capacitor. Now the DC source setup, here we have to analyze for any circuit analysis. First we have done with the DC analysis. Now we have to proceed with the AC analysis. Now the DC sources will set up here a DC currents as well as the DC voltages, which fluctuates in your transistor currents and voltages. So next, a simple way to analyze the action of your transistor amplifier uh, is to split the analysis into two parts. So first one is the DC. First we have to take the DC equivalent circuit. Thereafter we have to take the AC equivalent circuit, and we'll do separately the DC analysis as well as the AC analysis. Now, when you are doing the DC analysis, we have to open circuit your all the coupling capacitors and your bypass capacitor as well. So, and the AC signal source must be grounded. So, while you are performing your AC analysis, we have to ground the DC signal source to ground. So, we have to ground your DC signal, as well as we have to short circuit your capacitor, coupling capacitor. Since for an AC signals, the reactance offered by those capacitors is very less, so it is treated as a short circuit. So now, like this, in two way, we will analyze your CA amplifier stage. So now, while you are doing your balancing circuit, we have completed our DC analysis. How to draw the DC load line, and AC load line is also drawn by just grounding your DC signal source and by calculating the currents, AC currents which are flowing through that transistor, and the voltages due to the applied AC signal input, that we have to calculate it. Now, when you are drawing the DC equivalent circuit, so the thing is here only the DC signal conditions are considered. So, and you have to assume that there is no AC signal is applied. So for this purpose, we have to connect all the AC sources are reduced to zero, as well as all the capacitors are considered as open circuited. Next, if we carefully apply these steps to a transistor amplifier, we shall get your DC equivalent circuit. As well as to perform your AC analysis, so when you wanted to draw the AC equivalent circuit, so only we have to keep the AC signal conditions are considered, and so in order to do the AC signal conditions, first we have to reduce the DC source to zero. So it means the DC signal source must be grounded, as well as your capacitors are considered to be shorted. Since we are doing your AC analysis, so for the applied input frequencies, you have to treat your reactance offered by those coupling capacitors and emitter bypass capacitors are very less, and those are treated as a short circuit like this. So we will perform your AC and DC answer. Now the load line analysis. So now in a biasing we have just learned about your DC load line. The same manner we will also calculate your AC load line by using the methods of your DC analysis and AC analysis. Next, so how to calculate your voltage gain and power gain. So in a DC analysis, the voltage gain is the ratio of your output voltage gain to input voltage gain. So for a CE amplifier, so it can be easily provided voltage gain is equal to output voltage to input voltage, where the output voltage is equal to IC into RAC, where RAC is the effective output load resistor, and that effective output load resistor is equal to RC in parallel with the load resistor or the output resistor or output resistance of the transistor R0. So now R0 is larger than your RC. So the amount of the amount of resistance at that R is the effective load resistance approximately equal to RC. So now here the voltage gain can be, if I included that output resistance of the amplifier also, so then it is equal to IC into RAC divided by the input voltage of CA amplifier is treated as IB into Rin, input resistance. Rin is your input resistance. So IC, the ratio of output collector current to the input base current is nothing but your beta, which is called as a current gain, DC current gain. So hence the voltage gain is equal to beta into RAC divided by Rin. So now RAC is the effective collector load and Rin is the input resistance. Next, the ratio of next. Now to calculate your power gain, we have to calculate the output power, the ratio of output power to the. We have to take the output power to the ratio of output power to the input power. So for a CE amplifier, it can be provided that. So here the output power is calculated like load current into of resistance, square of your load current. So now our load current in common emitter is collector current. So IC square into RAC divided by input power is IB square into Rm. So IC divided by IB whole square is nothing but here the amount of DC current gain, which is multiplied twice. So it is beta square into RAC divided by Rm. Next, these are the quantities so which you are representing. So in order to represent the DC quantities as well as AC quantities, so let me take the AC and DC quantities are usually represented by its capital letters. Your DC stable voltages and stable currents are represented with I and V. So currents in the I with I and voltages are with VC, as we have three terminals and definitely we have here three currents and three voltages. So if it is a DC quantities, then these are represented with non-italic as well as the subscripts are represented with the capital letters. So which denotes I non-italic I represents the DC current, non-italic B represent the DC voltage, and the subscript, which is capital letters, represent those corresponding terminal currents and voltage. So IB means base current, IC is the collector, IE is the DC emitter current, VC is the collector voltage, and VE is the emitter voltage. VC is the collector to emitter, like this, VBE base to emitter. So these are only due to the applied DC analysis, so which are representing the DC quantity. Next, AC quantities are represented with the italic subscripts, and those subscripts are represented with the small letters. So IC is AC collector current, IE is AC emitter current, IB is the I suffix small letter B indicates the base current, and V italic letter V with the subscript small letter C indicates the voltage at collector terminal. So where VCE represent the voltage at collector to emitter. So if I am doing a AC analysis, so AC quantities may be represented in RMS, or average or peak to peak. So RMS values will be used unless otherwise stated. So next, AC instantaneous quantities are represented by instantaneous quantity. So at this particular point, if I need the current, so at this time interval, if I need the current, the instantaneous currents are represented with a small letter. Instantaneous quantities are represented with small letters, and the subscript represent that corresponding terminal currents or voltages. So IC is the instantaneous collector current, IE is the instantaneous emitter current, IB is the instantaneous base current, as well as VC is the instantaneous voltage at that particular time. So next, resistance is also identified with the AC resistance are identified with small letters, as we are representing with a subscript which is with a small letters only. With a small letter R indicates the AC resistance. So small r indicates the AC resistance, and the subscript for each letter of small letter R indicates the resistance which is offered at that particular terminal. So RE represents emitter resistance, RB represents your base resistance. So like this, we'll have these quantities which you are going for the analysis purpose of your CE amplifier. Now coming to this linear amplifier. So this is a simple CE amplifier using a voltage divider network. Now in this simple CE amplifier, what I'm going to analyze here, DC analysis as well as here AC analysis. So now here just look it out here. So this VCC in addition with R1 R2 forms a voltage divider RC network as well as here RE. So next, these coupling capacitors C1 and C2. C2 is used connected at the output. C1 is connected at the input. So input, in order to couple your signal source to the base of your transistor, we have used a C1. Whereas to take out the output from the collector terminal, we have used one more coupling capacitor at the collector terminal, and then we collect your output across this load resistor RL. So next, emitter resistor we connected at the emitter in order to compensate the amount of increment of collector current or a decrement of collector current due to the temperature increase. So we connected here RE. As well as we should also connect one more capacitor, so which is called as the emitter bypass capacitor. So let I treat that as a, so in shunt with your RE. So this is your capacitor which is connected in a CE amplifier. CE is your emitter bypass capacitor. So with this connection of these three coupling capacitors at base, collector as well as at emitter terminal, in addition with the voltage divider, can form a CE amplifier. So now a linear amplifier provides your amplification of your signals without any distortion. The output is exactly the amplified replica of its input signal. But so we have just verify here, this is your voltage at the base terminal. So now the weakest signal quiescent voltages, VB is the AC signal voltage, where VBQ is the, so this is the DC operating voltage at base of your transistor due to your VCC. So on this DC level, your input is superimposed, and that is applied at your base of your transistor. So then if I am applying that voltage, then obviously we have the base current. So AC current IB, where the DC current IBQ quiescent operating base current is IBQ. So which is flowing, so your output current is superimposed on your the quiescent current base current. So now your collector current quiescent value due to your VCC, and this is your amplified output due to the applied VCC. So we have the amplification. So this weakest signal is amplified due to this connections of your R1, R2, RC as well as your RE. The amount of the strength of the collector current is increasing, but they are in phase. So IB and IC are in phase, whereas the voltage, so VCE, here it is at out of phase. So collector to emitter, only the collector to emitter voltage is having the 180 degrees 180 degree phase shift, or let me define that as your output is out of phase with your input signal. So for a positive signal, you are getting your amplified level of your voltage, but with a shift of 1. For positive, you are getting negative. For the negative signal of input, you are getting your positive voltage, amplified voltage. So like this. So these are the notations which I am going to utilize for the DC as well as your AC analysis. Next, the coupling capacitor blocks the DC and prevents your the source resistance RS as well as your RA, which changes from your DC bias voltage at the base and collector terminal. So hence we connected C1 here as well as C2, and then CE is connected in order to transfer your AC collector current through this coupling capacitor. So AC collector current, when it is passing through there, so it also passes through RE. So due to that, that amount of ICRE is very high. If IC is maximum, then drop across this become maximum. So then the effective amount of base voltage, the total amount of base voltage VB is equal to VB is equal to VB is equal to VBE, base to emitter junction voltage, plus of VE. So if it is increasing, then the coupled voltage, base voltage reduces. So here the base current is reducing. In order to avoid that, so we have to connect one coupling capacitor. So this coupling capacitor can bypass that AC collector AC collector current. So because for the applied AC, if a AC collector current is transferring, then this capacitor is simply, it is acting like a short circuit. So when you have a small resistance path, so instead of your the current chooses here the low resistance path, instead of your it is transferring through RE, it will bypass through the capacitor C. So with that, so amount of voltage drop, the increase in the voltage drop in RE can be reduced. Right. So next, is it clear everybody? Operation of your CA amplifier. Is it clear, Nana? Do you have any doubts? Do you have any doubts? Any doubts, Nana? Can I move to your next slide? Till this, is it clear everybody? So why we connected your biasing circuit, why we have connected your coupling capacitor and bypass emitter bypass capacitor? Right. Now, so AC load line, like your DC load line, how we have drawn, in the same manner, we have to draw a line on your output characteristics. So by taking your VC is maximum at maximum with a node B, and as well as your collector current, which is on y-axis, which is a saturated voltage. So on this one, so your AC signal is superimposed. So this is your AC signal. Just everybody look here. So AC signal is superimposed on your input signal. So when it is in superimposed, the amount of current flowing through the base is IB. So this is your quiescent value of your base current due to your DC. So and this is your collector current. So when you transfer the base current, so through the input signal source, so our output collector current is amplified. So which are having the same same phase. So IB and collector current are in phase. So whereas this also it is superimposed on your quiescent value due to your DC biasing. So your AC collector current is transferring through the collector terminal. Then amount of voltage drop across your RC. So which is VCE. When we are calculating VCE. So VCQ. So on the quiescent value of your VCQ, the AC voltage will be superimposed. So so which is having the 180 degree phase shift with respect to your input voltage or signal input voltage. So positive, negative you will get it. For negative signal you are getting your positive output AC voltage. So now like this we will do your AC analysis. So next thing is here. What are the DC voltages and quiescent values? So practically we would have. So how to calculate those quiescent values and how to calculate that amount of output voltages and the output AC collector current, that we have to do it. So common emitter amplifier. So 180 degrees phase shift will get it at the output. So V in and V out are the notations which I am going to utilize for input as well as at the output. So CE amplifier has high voltage gain, high current gain. So generalize. So if I prefer the amplifier means, so I have to prefer the CE configuration, since the characteristics of CE configuration is all are moderate values. So input resistance high, output resistance low, and current gain and unit your voltage gain are moderate. So are high. So compared to the three configurations. So generalized amplifier means, so you have to use your CE amplifier. Now this is the process how to do the DC analysis. So I said you how to do your DC analysis. While you're doing your DC analysis, so we have to ground the AC signal source and we have to open circuit your coupling capacitor. So your left part of your, I'm just going to the circuit slide. So just you compare the circuit slide with this. Just to see here the circuit slide. So left part of this circuit, which included one signal source, one source resistance, one coupling capacitor, are just replaced with a open circuit in my DC analysis. So there is no AC signals or AC signal source, the series resistance of signal source as well as your coupling capacitor. Only we connected your resistors R1, R2, RC, RE, and here also the bypass capacitor coupling capacitor at emitter is also replaced with the open circuit, and at the output terminal we also have a coupling capacitor CC. So C2, that is also open circuited. So now when I open circuit all the coupling capacitors and here, so just grounding your AC signal, we are doing the DC analysis. Now in order to do this DC analysis, we have to use the Thevenin equivalent circuit at the base, because our VCC is transferring to a voltage divider network. So if I use the Thevenin equivalent circuit, so then it is easier to simplify to calculate your input currents as well as your input voltages. So now in order to do that, we are using your Thevenin theorem, right? So always you have to take the base input resistance must be greater. You have to choose the values of. So this is the design part of your CE amplifier. So most important thing is the base input resistance of a transistor must be greater than 10 times of your R2. R2 is the one of the resistor at the potential divider network. So then we have the that operating point will be fixed at your center of the load line. So otherwise it will be moved. So for a stiff voltage divider network, so we have to take the base input resistance must be greater than, for example, now, so this is for example 1K and this is 10K. So our input base resistor is of 100, for example, now I am taking it as a 50 kilo ohms. Then I should take my R2 which is equal to 10 kilo ohm. So like this, so if I am taking 1 kilo ohm, then it will be 10 kilo ohm. So if my base resistance is 50 kilo ohm, then it will be R2 if I choose with 1 kilo ohm, so then it will be 10 kilo ohm. If I choose your R2 with for example, if I treat with 10 ohms, then it will be 1 kilo ohm. So 10 ohms, if I'm taking it as a 100 ohms, then it will be 1 kilo ohm. Where base resistance, if I have that as a 10 kilo ohm, then I can choose the R2 value with 100. Then it will be only 1 kilo, right? So now let me calculate what is the base voltage using a DC analysis. Now the base voltage is a voltage across here resistor R2. So now we have to calculate the voltage drop across here resistor R2. In order to find that voltage drop across here R2, let me take the total amount of current passing through the, let I take this as a I1. So passing through your R2. So this I1 is due to your applied VCC. So I1 must be equal to VCC divided by R1 plus R2. So now when I wanted to calculate your base voltage, then I have to multiply this current with your resistor. So passing through your R2 is I1, hence the voltage drop across here resistor is nothing but VB. VB is equal to I1 into of R2. I1 into of R2. So I1 is VCC divided by R1 plus R2 into R2 is VB. So now if I substitute those values, then I would have the base voltage is equal to 2.83. So now in order to find your emitter voltage, to find your emitter current and base current, so we have to have this voltages emitter. What is the emitter voltage? What is the base voltage? As we know that so this amount of base voltage can lead your base to emitter junction to forward, because my base voltage is equal to 2.83. So base to emitter junction is your cutting voltage is, if it is silicon, then it would be 0.6 to 0.7. So in order to find this, so this base VB is equal to, base voltage is equal to VBE plus of VE, where if I wanted to find your VE emitter voltage, so I have to subtract VBE from base voltage. So VE is equal to, so here you have VE is equal to VB minus of VB. As we know that VB is, we calculate as 2.83 volts with the given resistors and with the magnitude of VCC. Only for this we have this VB equal 2.83 volts minus of VB, it is constant because it is a silicon transistor. So 0.7 volts. So if it is germanium, then you have to replace this 0.7 volts with 0.3 volts. So then we have 2.13 volts is the emitter voltage. Now in order to find your emitter current, so let I take that ratio of your VE with respect to your emitter resistor. So VE divided by RE will give you the emitter current. So 2.13 divided by the total amount of emitter resistance is 560 ohms. So then emitter current is equal to 3.8 milliamps. So this is a common emitter amplifier. As if I neglect the base current, since the base current is in the range of microamps. So IE is equal to IC plus IB. So IE approximately IC if I neglect the base current. Hence IC if I consider it as approximately equal to IE, then the collector voltage, the total amount of collector voltage. So collector voltage is collector to ground. So the voltage which is calculated at the collector terminal is here collector voltage. So which is collector terminal to ground. So VC. But this VC is, so VC which is VC is equal to VCC minus of IC RC. So now this is equal to, so 12 minus, so as IE is approximately equal to IC, so I have considered IC is equal to 3.8 milliamps and RC value is equal to 1 kilo ohm. So 12 minus 3.8 will get the VC voltage is equal to 8.2. But VCE collector to emitter voltage, if I want this voltage, if I wanted to find VCE collector to emitter junction voltages, if I wanted to find, then we have to take the, this V total is VC, where VC is equal to like this. VCE plus of emitter voltage, VCE plus this is minus, so plus and this is minus, so VCE plus of, and the amount of voltage drop across this RE is here VE. So here when I wanted to find collector to emitter voltage, I have to subtract my emitter voltage from the collector voltage. So VC minus VE will give you the collector to emitter voltage. So now the collector to emitter voltage is equal to 6.07 volts. Since we know that collector voltage is 8.2 and emitter voltage we calculate it as a 2.13 volt, 2.13 volt. Hence our collector to emitter voltage is equal to 6.07 volts. Now, like this, we'll do the DC analysis of common emitter. Then AC analysis of common emitter amplifier is performed by connecting your DC source to ground, and all the coupling capacitor must be shorted. So since your bypass capacitor is filled as shorted, so now we are just having a parallel combination of your emitter resistance with your reactance offered by the capacitor is 0. So hence your emitter terminal is grounded here. Bypass, since bypass capacitor is shorted, the amount of resistance at that emitter is the parallel combination of RE with your reactance offered by the bypass capacitor, where bypass capacitor is reactance is 0, since your resistance offered at the emitter is 0. So in an AC analysis, the emitter is replaced at the emitter, that emitter resistor is replaced since your bypass capacitor is shorted. So now coupling capacitor, there is no coupling capacitor as this is shorted. Here output coupling capacitor also replaced with a short circuit. Next, the DC signals are grounded, hence this R1, so one end of R1 we connected to the DC signal. DC signal while we are doing DC analysis, but in an AC signal, that VCC, what you have VCC, that must be grounded. Hence this R1 other end is connected to the ground. So now here, so now we'll do the AC analysis. How to do the AC analysis? So this is the part of your actual analysis of your how to connect your resistors at the input as well as your at the output of collector term of your CE amplifier. And we have to choose the coupling capacitor of C2 must be large enough so that the reactance offered by the capacitor is very small. So C2 value, coupling capacitor C2 value must be large enough so that reactance offered by the capacitor which will be very small when I compare with your emitter resistor. So only this is the node we have. So reactance offered by the capacitor value which I am taking as C2 is must be large enough, then the reactance of the capacitors become very small when I compare with your emitter resistor R. Then No AC voltages can be developed across it, so it appears as an AC short. So this is why DC source is called an AC ground. So here doesn't have any DC signal, so that is connected to the ground. Hence, it is also called named as a AC ground. So AC equivalent circuit of CE amplifier is the image shows this AC equivalent circuit. Now we'll do the AC analysis. We'll find here what are the currents, input currents, output currents. So now first let me start with your input resistance. So total input resistance. Now here when I wanted to calculate the total input resistance, so R1 is in parallel with the R2 in parallel with your the base resistance of your amplifier. Hence here the next slide we have just taken R1 in parallel with R in the total input resistance is equal to R1 in parallel with R2 in parallel with the input resistance of the CE amplifier at the base. So base is my input, hence I have mentioned it as a input resistance at base. So input resistance of base input circuit CE amplifier is equal to beta AC into RE dash. So this we can get it using your simplified RE model. So simply in a simplified RE model, we'll have the input resistance is equal to beta AC into RE dash, where emitter RE dash is the AC emitter resistance. So and also we can also represent that as Rn is equal to ratio of our AC base voltage with respect to the AC base current IB. So we can also replace with VB by IB, or directly if I'm using a simplified RE model, then I will replace this with beta AC into RE dash. So if I include the series resistance RS, then our total input voltage, so with the RS is, so your series resistance, your source resistance RS is in series with your total input resistance, hence the base voltage. So now the the total input resistance is far larger than your source resistance, hence, so almost the output now, let I'm reading, this is your RS and this is your R in total input resistance, the total input resistance of CE amplifier. Now this is your VS connected, AC signal where we connected. So now this is your base voltage. Across here Rin will calculate your base voltage. So base voltage is calculated across the total input resistance. So this is your RS. So when comparing the value of source resistance with your input total input resistance, so it is far larger. So this is very small. So then the amount of, in a series circuit, the amount of voltage drop will be more in input the total input resistance than in the series resistance, source resistance RS. So source resistance RS. Hence here VB is equal to R in total divided by RS plus R in total into VS. So as RS is far less than your the total input resistance, hence here, so just ignore your RS. If I ignore the RS, then R in total and R in total are cancelled. Then applied base voltage approximately equal to the amount of AC signal source. So this is nothing but your input you are applying to the base of your amplifier. Next, the output resistance of amplifier is output resistance is treated as R out is approximately equal to the collector resistance RC. Our output resistance of voltage divider bias circuit is the resistance looking at the collector terminal. So now that collector terminal output resistance is approximately, because we shorted here coupling capacitor, so there is no such reactive element over there. Hence, the output resistance is approximately equal to the collector resistance RC. Now, if I am collecting the output across the load resistance, then I have to take the effective load resistance, so which is the parallel combination of your RC and RL. Now this is your AC analysis. How to draw it. This is the output equivalent circuit, and this is the input equivalent circuit. What you have, AC equivalent input circuit and the AC output equivalent circuit. And from this one, so we'll find your output voltage gain. So V out by V in, VC divided by VB. As VC is equal to IC into RC, IC is approximately equal to IE. We replaced with IE into RC. Now VB is equal to IA into RE dash. So AC resistance we have here. So now IE into RE dash. So AV is equal to IE cancelled. Then we have RC divided by AC emitter resistance RE dash. Next. This is the voltage gain if I consider your signal source. So overall voltage gain of the amplifier. So AV dash is equal to, actually we'll take the overall voltage gain as output to, it is a ratio of output to input. If I consider the signal source, so just in the last slide we have just considered the base voltage as the input voltage, the effective input voltage of this transistor. Now if I consider the overall voltage gain, so I have to choose here, I have to consider the series resistance of the source RS. Hence, so Vs is also considered. Hence here output of this become VB divided by Vs at the input side, whereas at the output it will be VC divided by VB. So now here AV dash overall gain is equal to VB by Vs into a VC by VB. As we already know that what is VC by VB is AV, and VB by it is equal to VB by Vs into AV. So as VB cancel, we can also represent it is equal to the overall voltage gain is equal to ratio of our collector voltage to the signal voltage, magnitude of the signal voltage Vs. Next, a common collector amplifier. So how to construct a common collector amplifier? Input is applied at the base and the output is collected at the emitter terminal using your coupling capacitor C1 and C2. And this is most popular as a buffer amplifier, since it is having the high input resistance and low output resistance as well as high current gain. So we could use this as a buffer amplifier, and not that high input resistance is very useful to minimize your loading effects, especially when the circuit is driving with a low resistance loads. So now, so this is your simple circuit. Why it is having the low voltage gain is one is, since we are applying the input at a base terminal, and here the base voltage is approximately equal to the emitter voltage. So there is a transparency from your output to the, we are collecting the output at emitter terminal and we are coupling the voltage at base to emitter junction. So base to emitter junction, only one junction is forward biased here. So base to emitter junction is forward biased. So whatever you apply at the base, that will be transferred to the emitter. So hence the output voltage gain is VE divided by VB is approximately equal to 1. So the only one configuration which is having unity voltage gain is here CC, as well as with the high input resistance. Next, so these are the AC, how to find your DC analysis as well as your AC analysis of your common collector amplifier. So this common collector amplifier is like your it is almost replica of your common emitter. Only the thing is here we just take the output at your emitter terminal. V out is equal to IE into RE, where Vn is equal to IB into Rn base. So In is equal to IE into RE dash plus RE, where RE dash is your AC emitter resistance. So hence voltage gain is equal to output V out divided by V in. So V out is IE RE divided by IE into RE dash plus RE. So RE by RE dash plus RE, as this RE resistance, emitter resistance is AC emitter resistance is small RE dash, and DC resistance, so the connected resistance which are RE, effective resistance emitter resistance is equal to RE in parallel with RL. Sorry for the interruption, Anna. So there is a network issue. So just now the net is dropped. Internet is dropped. Right. So output resistance is equal to approximately equal to RS by beta AC in parallel with your RE, and the current gain is equal to output current to input current, IE divided by IN. So power gain is, it's a product of your voltage gain and current gain. So almost your voltage gain in your common collector is 1. Hence power gain is approximately equal to the current gain in your common collector amplifier session. Next, common base amplifier. So here we connected the AC signal to the emitter terminal because base is common, and we have to take the output from collector terminal. So common base amplifier. So this is a configuration for the common base amplifier. Base is connected common, and you have to apply the AC input signal at the emitter terminal and collect your output at the collector terminal. So we have provided your voltage divider balancing, and this is your AC equivalent circuit of your common base amplifier. So base, emitter, base is connected to ground, emitter is connected with the VIN, and effective input resistance is RE. So RE dash is the AC input resistance due to your base to emitter junction PN junction diode. The dynamic resistance in between that input junction is treated as a AC emitter resistance RE dash. And this is your output current which is passing. We have just replaced that collector terminal with the current source. So IC, the AC amount of current IC. So output resistance is, the effective load is equal to RC in parallel with RL. So like this we also do your AC analysis for this common base amplifier, and we'll find your power gain as well as your voltage gain. Next, coming to your multi-stage amplifiers. So this is about your single stage. Actually, we have to learn about only CE amplifier. Just for a briefing purpose, I just gave you the CCA amplifier, how to construct it, as well as your CE amplifier. Sorry, CB amplifier. Now, multi-stage amplifiers, how to construct a multi-stage amplifier. So two or more amplifiers can be connected in a cascaded arrangement with the output of one amplifier. This is the output of first stage amplifier is connected as an input to the second stage. So the next one, so like this. So now I have a total number of amplifiers which are connected. Here it is n number of stages. So now this n number of stages are cascaded by connecting output. This is the symbol for an amplifier, negative feedback amplifier. So output is connected as an input, and second stage output is connected as an input to the third stage, and third stage is connected as an input to the fourth stage, and n minus 1th stage output is connected as an input to the nth stage amplifier. So now in order to find, so why we prefer this multi-stage amplifiers are, so in order to obtain the voltage, overall voltage gain, which is if we require a more amount of voltage gain, so then we have to connect these number of voltage amplifiers as a cascaded nature. So now the overall voltage gain, total voltage gain is stated as AV dash of cascade amplifiers. So it is the product of your individual voltages. So how to calculate your total voltage gain is AV dash is equal to AV1 into AV2 into AV3. If you have n number of stages, then it will be proceeded with the multiplication with the n number of stages AVn. So now if we all I already mentioned that your AC analysis is done with your frequency response characteristics. On that frequency response characteristics, we are taking the gain in decibels. So when you are mentioning the gain in decibels, so we have to convert the voltage gain into decibels by using 20 log of AV. So we have to calculate every individual these stages, single stage CA amplifier voltages gains must be first modified into decibels. Thereafter, the overall voltage gain in decibels can be calculated. So the overall voltage gain in decibels is calculated by just summing your individual voltage gains. So in decibels. So if you are mentioning your voltage gain, then you have to take the multiplication. So if you are mentioning your voltage gain of each stage in decibels, then you have to sum up your all the individual or single stage amplifiers. Then we'll get the overall voltage gain in decibels of a multi-stage amplifier. Right. Now, next I'll take a simple example. So in this simple example, now I have a cascade amplifier stage arrangement which follows the voltage gain. So first stage is having AV1 equal to 10, AV2 is equal, second stage is having 15, third stage is having the 20. So what is the overall voltage gain? So first you have to calculate the overall voltage gain, because in this multi-stage amplifier I have 3 stages which are cascaded. Also express, the next task is also express the each gain in decibels and determine the voltage gain in the overall voltage gain in decibel. So as the overall voltage gain is the multiplication of each individual stages, hence I am taking the product of AV1 into AV2 into AV3. So voltage gain is 10 for the first stage, 15 for the second stage, and 20 for the third stage. Hence the overall voltage gain in a multi-stage amplifier of 3 is equal to 3000. Whereas each gain decibels, if I convert, then it is equal to 20 decibels for the first stage, 23.5 decibels for the second stage, and 26.0 decibels for the third stage. Now, if we require the gain, overall gain in decibels, then I have to sum up all these gains which are in decibels. So 20 plus 23.5 plus 26.0 is equal to 16. The overall voltage gain of this 3 cascaded stage in decibels is equal to 69.5 decibels. Whereas if I represent with the voltage gain, then it is equal to 3000. So this is the end of your unit 2. So multi-stage amplifiers. So now let me take so next slide will be the construction of your RC coupled amplifier. So I have taken a two-stage RC coupled amplifier. So now just verify here. This is the single stage. This is your single stage CE amplifier, and this is a one more same single stage. The same components we have here: R1, R2, RF also 47, R6 also 10 kilo, R3 also 4.7, R7 4.7, RE is 1 kilo, 1 kilo, C2 400. So I've just I took two CE amplifiers and I cascaded by connecting the output of your first stage as the input of your second stage using a coupling capacitor. So C3 I took as a coupling capacitor to couple my output of the first stage as an input. So based on this coupling element, you have the resistive coupling, capacitive coupling, direct coupling, transformer coupling. So many amplifiers are classified based on the coupling element from one stage to the other side. So multi-stage amplifiers are classified based on the coupling elements. So now here I use the capacitor and resistor also are included. So this is your output collector resistance. So RC coupling, why we are calling it as RC coupling means, so you are coupling the input of your output of your first stage as an input to the second stage using your elements of resistance and capacity. Hence it is named as a RC coupling elements. So if I doesn't use any element here, then it might be a direct coupling. So if I just replace this capacitor with a direct connection, then it is called as a direct coupling. So now here the voltages, so DC biasing as same as the both stages are identical for a common emitter DC biasings, so which are we have discussed in a single stage amplifier. And while we are doing your analysis, so just to do your analysis of the first stage, and that you can apply to the n number of stages, and with that so we can also calculate the amount of overall voltage gain and power gains. So this is the simple calculations of your how to calculate. So this is your input resistance of the second stage, how to calculate by considering your R3, R5, R6 and R7. So multi-stage AC equivalent circuit for the first stage is shown in below. AC input resistance of second stage is like a load for the first stage. So RC1 is equal to, the load for the first stage is R3 in parallel with R5 in parallel with R6 in parallel with Rn base, because here just to see here collector resistance, R3 is nothing but collector resistance, R3, R5, since we are doing AC analysis, VCC is grounded, so R5 is also connected. So one terminal to this, okay, capacitor is shorted, R5 is other end is connected to ground, R6 is available and input resistance of the second stage. So like this we will calculate your the load resistor for the first stage. So R3 is in parallel with R5 is in parallel with R6 is in parallel with the input resistance of the second stage. So AD1 is equal to RC1 divided by RE dash. So next the second stage with the no, because it is a two-stage amplifier, so it doesn't have any load resistor here. Hence the load resistance of the second stage is equal to R7. So RC2 is equal to, the effective load resistor is equal to RC2 is equal to RC is equal to R7. So output voltage gain of the second stage is equal to R7 divided by RE, AC emitter resistance RE dash, which is equal to 197. So overall voltage first stage is having the gain of 68.5 and second stage is having the gain of 197. So approximately that overall voltage gain is 13,495 and in decibels it is is equal to 20 log of this 13,495 is equal to 82.6 decibels. So now I said you that, so using your direct connection also you can couple your input, then that will be known as the direct coupled multi-stage amplifier. Now, why we have just replaced this capacitor at the input is because in order to obtain the low frequency response, a very good low frequency response. So this capacitor can affect the low frequency response. So in order to avoid or to improve the low frequency response in a multi-stage amplifier, you could also use the direct coupling. So hence that we have just replaced that capacitor with a direct connection. Since that coupled capacitor at one stage or second stage will lower the low frequency response of your multi-stage amplifier. Hence, we replace that with a direct connection. So this is about your basic knowledge of your multi-stage amplifier, how to calculate your overall voltage gain, and how to calculate the gain in decibel, and how to construct your RC coupled multi-stage amplifiers. So with this, we have finished our unit 2. So in the next session, so we'll start your third unit. Now you can attempt your quiz. After attempting your quiz, you can log out. Thank you, Nana.